These are my, we're studying a core collapse supernova problem. You've heard a few things about that already, including some stuff during the plenary session. It's sort of unexpected. There you go. We have a number of collaborators on the work I'm going to be showing you today, most of which was done on not blue waters. But these are also our collaborators for our PRAC project that's just starting up. So why do we want to study the core collapse supernova problem? Well, we know that some stars explode. As you heard, they go look every night and the stars get bright, and if you go back and look at the images, you can find some where the stars have disappeared clearly. So nature does this pretty well, and in theory we're having a bit more trouble. And we want to understand, how does that collapse of the core result in an explosion? How do you transfer, a few percent of that total collapse energy into the rest of the collapsing star? It's also an opportunity to understand, to work with some exotic physics, general relativity, nuclear matter, neutrinos that are transporting energy. These are fairly rare things. And we have the neutrino and gravitational wave signals in addition to the normal observational astronomy things. And also, the core collapse supernovae are important contributors to the heavy element abundance in the universe and are critical to making planets like ours. And so after the core collapses and forms this proto-neutron star, at the center we have this sort of cartoon picture of what's going on. There's a dense opaque neutron star from which neutrinos are slowly diffusing. Some of those neutrinos are absorbed in the layer just above it, and there's a matter continuing to accrete on top of it, and then you get these convections and shock oscillations and such things. And there's a lot of physics that's actually happening inside the real supernova. And I've listed it, most of them on the left side. And then when we're building codes, we want to represent that physics inside our code. And so I'm going to be covering two parts of it with a little bit more detail. The variation in the stellar models that go into the simulation, and then how dimension and resolution of the grid impact the result. And so we do this in our group with a code that we've constructed called Chimera. It has all of the all of those pieces of physics at some level of approximation. They're reasonable approximations, but all of them could of course be made better. So it's a computational sort of environment. I'll tell you a little bit about some of the computational elements. For the simulation I'm going to show you today, it's 540 radial and then 180 in theta and phi. Spherical polar grid, and we sphericalized inner core to help constrain our time steps and keep them from being under too tiny. So this is just a uniform resolution around the equator, 2 degrees. And to also control the Courant condition, we've implemented a grid that's uniform in the cosine of theta. And this gives us a couple of fairly wide zones at the pole, but good resolution in most of the rest, as low as 2/3 of a degree. This turns out to be a fixed solid angle grid. The hydrodynamics that we're using are dimensionally split, so we have these transposes, and these are implemented with MPI all-to-all using subcommunicators on subdomains. So we have 180 different subcommunicators involved in this particular simulation, about 32,000 MPI ranks. This is run on 4,000 XK7 nodes, 8 tasks per node with a little bit of MPI. That gives us about a 10 to 15% boost. We used XK7 nodes because we were running this on Titan, not on blue waters. But I have been running on Titan using the XE6 nodes, and it works just fine. So one of the important aspects of this problem is that while the problem is truly three-dimensional, there are no symmetries in it. For computational reasons and expediency, we have worked in lesser dimensions. And universally, one-dimensional model, spherical symmetry, fails. And you can see that with the red line. This is the shock. It goes out. It recedes. It was in a couple of earlier talks. And then if you look at 3D versus 2D, the earliest work that was done in Adam's group showed that 3D was favorable to getting explosions, and some of the later work with other parameterized models have shown the opposite. And the 3D being harder has been borne out in basically all of the rad hydro simulations like the ones we're doing here. And you can see that in our model. So this is, in effect, the key result from the paper. And there's, oh, it's off the bottom. And that is, it takes about 250 milliseconds for the 2D model to turn into an explosion, and it takes about 350 for 3D. And when it does, the shock growth is more vigorous in 2D. So if you want, you can say that this is not a good thing because we're still not completely at the observational level for our explosion energies. I'm going to show you a movie in a minute because movies are fun, and you learn a lot from them. But on this slide, I'm going to introduce what's happening inside of our simulation. The 3D simulation is on the left, a nice volume rendering of the entropy. This is before either of the models explode, and we have a lot of small-scale plumes in the green. And then in the middle, we have a slice along the pole, and we can see there's a lot of plumes rising and a lot of difference in scale. And on the right, there's a 2D simulation at the same time. All three of these images are at the exact same spatial scale at this point. And the 2D critically only has a few plumes, and this is part of that 2D character that was mentioned this morning. At 300 milliseconds, the 2D model has gone into explosion, and its scale is different, and it now is dominated by two large plumes in the accretion stream near the equator. In the 3D, we have 2 or 3 large plumes that you can see in this particular slice, and they're mapped, and you can see them in the volume render where we have some hot material showing up as red. I want you to pay attention both in the images here and in the movie that follows to the plume on the upper left side, which will be the plume that sort of wins the race.
Why do your hemispheres not match in 3D?
This is a spherical polar grid, so the zones meet at a point, and they're 180 degrees out of phase. And the zones are particularly wide, so it looks particularly ugly. This is true of any, this is going to be true of any grid that comes to a point at the pole. And I've noticed in looking at some of the other people's work that they like to do equatorial slices. I just didn't like our equatorial. I liked that it matches our slice here. So that's just 300 again. At 400 milliseconds, we have an explosion in both models. And the plumes become very large. And through time, the plumes, the relative scale of the plume is becoming much larger in the 3D. The other thing that I want to mention at this point is that the shock in the 3D model, which is the light blue surface, is an accretion shock. And as material falls through it, it flows right behind the shock and wraps around this plume. And around 350 milliseconds, so in between these two images, it falls into a pole, an accretion stream at the opposite end, and it obtains a preferred direction, as was mentioned this morning. So one of the things that we're seeing as the explosion develops is that the scale of the plumes is growing. And another way to look at it, other than the images I showed you in the movie that I couldn't, and in the questions I'll see if I can find it on my files, is that the scale of the plumes grows. And so this is a spherical slice of the radial velocity at 150 kilometers. And we start out at 200 milliseconds with a lot of smaller plumes. And as time progresses, the plumes become less numerous and larger. And this happens before the explosion develops. And this seems to be related to the development of an explosion and development of a plume that's able to sort of win that fight against the accreting ram pressure. So what we have been doing on blue waters is to look at resolution. This is sort of warming up to our full project. So on the left, I have an image slice out of that same 3D model at 250 milliseconds before the explosion starts. And on the right, I have one with just a straight up standard 2-degree grid. In this one, so we only have 90 zones from pole to pole, so it's half as many zones. At this point, I can't really say that there's a significant difference between the two. There's a lot of analysis that needs to be done looking at the shock radii and the development of the scale of the plumes, et cetera, in a more quantitative fashion. And there's a third simulation at 3-degree resolution that I had to restart this morning. And it's actually running right now on blue waters. But the 2-degree simulation is roughly the resolution used by our German competitors. and the 3 degree by our Japanese colleagues, or competitors, if you like. And so there's a lot of effects. There was some mention made in previous talks about particular direction, more favorable or less favorable as dimension changes, but there are a number of things that could impact not only the turbulent cascade, but as these accretion streams are going down, where are they dissipated? And you don't want to dissipate them too early. The explosions take a while to develop, and this is something we've known for a while, but we've explored explicitly in a recent set of 2D simulations that have been submitted to the journal and are under review. So the dashed lines represent the growth of the explosion energy with time with this particular measure. Now this is just the energy of the material in that expanding bubble. And then if you apply the correction for the binding energy of the material outside, you get the solid lines. And even those are starting to turn over and flatten out, though at least one of the models is not sort of ready to be finished. And so if you want to find out what the final explosion energy is, you have to run for a long time. But if you take the final points from those lines and you plot them against some observations, which are the colored crosses, you get the black dots on the left panel. The arrows represent a sort of crude estimate of an upper limit on the energy by taking the final growth rate for another second. And the two of the points sort of fall in the data cloud that you can see there. The other two are a little bit lower by a factor of 2 or 3, depending on how you want to view this plot. On the right, we have nickel 56, which is an important and relatively easy to observe radioactive isotope. And the data points fall very nicely inside that range. So our PRAC project and why we're on a run on blue waters is that we want to do the same kind of thing that we've been able to do in 2D, in 3D. We want to run multiple models and build a range to cover the range of the progenitor space. And we know that we have to run for quite a long time to get to the kinds of information that we want. Ejecta properties, explosion energies, neutrino and gravitational wave signals, and then at the same time sort of build up this library, if you like, of simulations that are very similar in their construction. So we can see if behaviors like that preferential axis are an artifact of resolution or even the fact that we have a pole. And in addition to this, we are very interested in computing the generation of new elements and isotopes in supernovae. And these are an important part of understanding how the universe evolved from the Big Bang to the present time in terms of the composition. And so Christian mentioned this paper before, but in this week's issue of Science, there is a paper showing that the titanium distribution in 1987A is asymmetric. Again, this is not surprising to theory. The green blobs on the bottom of this image represent places that are rich in titanium-44 in one of our 2D simulations. They come from not quite what you read in the first line of the abstract of their paper. They're not from a thin layer right above the neutron star, but they're from the margin of the expanding plume and from some of these streams falling down that get cut off and pulled into the ejecta. And we have a paper, a student is writing that. So we're planning to build a 3x3 grid. So it's a big grid, covering roughly 3 abundance levels, or metallicities as we like to call them, with 3 masses, run out for a second, using a 1-degree yin-yang grid, which has the advantage that there's no pole. It has much better time step restrictions, and we think 1 degree will be, that's pretty good. And that's actually achievable with the blue waters time. So thank you.